We discussed arithmetic groups last time, and so now basically I want to delve into the classification of arithmetic hyperbolic lattices, to discuss some non-arithmetic constructions, and then probably also we will discuss some like arithmeticity criteria for hyperbolic lattices, and in fact what are the geometric approach to arithmeticity. So let me just start with the following lemma. In fact, if I have to, it's just the lemma which gives rise to the following short observation, that there are infinitely many commensurability classes of arithmetic lattices. So I assume that I have two arithmetic lattices of simplest type. So let gamma I be an arithmetic lattice of simplest type. So this means that gamma I, okay, let it be for now just PO F I, where this PO is taken with integer coefficients of the field Ki. So I'm writing here where Fi is an admissible quadratic form over the field Ki. So then, then gamma 1 is commensurable to gamma 2. Okay, let me just remind that this word means that Fi sigma is positive definite for every non-identity embedding of the field Ki into R, right? So that the associated algebraic group POF in real points becomes a compact Lie group, right? So then I can say the following. Then gamma 1 is commensurable with gamma 2 if and only if K1 is equal to K2. And in fact, these algebraic groups should be isogynous to each other, but this can be reformulated in the sense of in the setting of quadratic forms. So this is the same field, right? And F1, okay, and there is some lambda such that lambda F1 is K isometric to the quadratic form F2, right? So this means that I can I can basically scale or by the way, this lambda should be from the field K, right? So there exists lambda from this field, which is now the same. It should be from the non-zero. It should be a non-zero element, right? I'm not going to prove this, but this just gives us some understanding of that. For instance, if I have forms defined over different fields, definitely the associated arithmetic lattices are not commensurable, right? But in fact, I can fix a field and choose infinitely many quadratic forms that are not. Okay, this is sometimes called that the forms are not similar over the field K or something like that. But in fact, yeah, one can think of just two quadratic spaces. So we have a basis associated with this form and with this form. So basically, up to scale, you need an existence of of the change of the transition of a transition matrix that allows you to move from one basis to another, right? But you also are allowed to multiply your quadratic form by any element. Okay, so yeah, just as a corollary, so we have the following consequence of this: infinitely many commensurability classes of arithmetic lattices of simplest type. Okay, arithmetic hyperbolic lattices, but in fact, you can apply similar consideration everywhere. Okay, so now it is interesting to discuss commensurability properties of lattices in general. And in fact, there is the following fundamental result of Weinberg. So as remember, I didn't tell you about the adjoint trace field, right? So I will do it right now. In fact, I will say that this the theorem, but in fact, it is a consequence of this theorem reformulated in our language. So let gamma be let gamma be as a risky dense subgroup of a real adjoint semi-simple. Okay, I think I can use the word simple, but yeah, in fact, it is true. Semi-simple algebraic group. So, for instance, any group like POF, POD1, or PUN1, or works. Yeah. Adjoint means it coincides with its adjoint image, or the same equivalently doesn't. It has trivial center, right? Yeah. So I will I will explain it a little bit here. So where it has trivial center. All right. So an algebraic group G, right? Then, in fact, I want to, I will formulate it that way. So, yes, then there exists and the number field K which is denoted as follows. Okay, it is defined as follows. This is U extended by the traces of the adjoint images of all gammas, where gamma is an element of gamma, and where the ad is the adjoint representation. So it acts where this is the classical notation for the Lie algebra of G. So the number field K and an algebraic K group and a K group. Okay, technically speaking, then one basically says that, in fact, this can be, there exists a basis such that this group can be defined over K, such that gamma sits in, but I will do it that way. So, and the K group V such that okay, V of R is my G, and okay, and up to conjugation, gamma sits in V of K. So then there exists the number field K and the K group V. So both K and V are commensurability invariants. So and up to conjugation. Moreover, K and V are uniquely determined. Okay, I want to, in fact, there is a subtle thing with K, sorry, with this group V. You can generally pass to, well, you can sit like in one adjoint class of this algebraic group V. So if you assume that V is also adjoint, then there is a unique such a group, right? So moreover, K and V are commensurability invariants. Are commensurability invariants of gamma. Okay, I will write it here. Of gamma and are uniquely determined. Generally, they are uniquely determined up to isogeny of V, but I can say that are uniquely determined. For V, I will write for V in its adjoint class, right? So technically, this means that, right, and I didn't, so this is called adjoint trace field. And this group will be usually called the ambient group. I will write it over here. Adjoint trace field and the ambient group. Ambient group V and the adjoint trace field K. All right. Okay, so now the following lemma holds. So if gamma is an arithmetic lattice, so if gamma is an arithmetic lattice, okay, so it's an arithmetic lattice in some absolutely almost simple algebraic group. Group G. So let me remind that there exists in general there exists an absolutely simple L group H such that gamma is commensurable with the integer points of this group L and so on, right? In fact, then so I will write here, right? i.e. gamma is commensurable with H L, where L is an algebraic number field. Okay, is an algebraic number field. H is absolutely almost simple, and there exists a surjective surjection from okay, I will write surjection from the product of H sigma of R for all embeddings of sigma to G with compact kernel, right? Just to remind what is the, so then that L coincides with that K. Then L is in fact the adjoint trace field. Okay, I will write it here. L is the adjoint trace field, and Okay, and in fact, it is totally real. And this group is up to isogeny the same as the ambient group from there. So this group H and well, it depends. I can choose. I can, in fact, consider H and V be connected, and then they also coincide, right? But assuming that both H and V are adjoint or connected, and assuming that we have H coincides with the V. Okay.
Okay. I were to take something like SLN-C09, right? My recollection from how superrigidities should work is that I should get a copy of SLN-C sitting inside any ether that that lattice sits inside. How does that resolve with this adjoint trace looking totally real? Simple. So it should be absolutely simple.
Yeah. Yeah, this is true in okay. Yes, you're right. This is going to be totally real in hyperbolic cases, in real hyperbolic case. But in general, okay, so even if it is a real algebraic group, yeah, it's not enough, right? I can, okay, yes, thanks. Let me remove this totally realness and leave a remark that in, so is a remark when for G being equal to PO dim1, right? Just to remind that this is the isometry group of the hyperbolic space. This holds when D is not equal to 3. So the above holds, I can say, whenever D is not equal to 3. Moreover, in this case, moreover, gamma, okay, K is totally real. Real, and in fact, the ambient group or the group of definition, in this case, they coincide. They can be, they are admissible in the similar sense as the quadratic forms. Moreover, it's totally real, and H with V is admissible, which means the following. it means that H sigma of R is compact for every non-identity embedding of the field K. So R and H sigma and H itself of R is isogenous to G, right? So in fact, I can write here that the connected component of H of R is isomorphic to the connected component of G, right? I will write this here with red. So in fact, I have that H of R connected component is, okay? So this means that in the real hyperbolic case, these objects become relatively simple. We have some field, totally real field extension of the field Q, and the algebraic group defining our arithmetic lattice in general should be the following. This algebraic group in real points for the initial embedding gives us just our non-compact Lie group, right? This one. Okay, up to isogeny. And for other embeddings, for all other embeddings, we get something compact. So in this product, right, in this product, H of, well, basically it was the tensor product or the restriction of scalars also, right? It was the restriction of scalars of K over Q H taken in real points. So we in fact have H of R times H sigma 1 of R times and so on. And this is in fact my G, right? Okay, well, up to isogeny, but I can assume that it is the same, times, and all this is compact, right? So this is our picture. So roughly, in this case, we have the following, right? Okay, so this is about, so basically this allows you get for any, the risky dense, yeah, and I should remind that all lattices are the risky dense in the corresponding Lie groups. So this gives us an opportunity basically to distinguish commensurability classes of lattices in particular. You just need to construct this field. In some cases, like for instance, for reflection groups, this construction is quite concrete, I would say. So let us discuss how does it work for reflection groups. I also remind that it was a general, why people were interested in reflection groups. They gave first examples of non-arithmetic lattices. In fact, it was an open problem to find those in hyperbolic spaces, even in dimension 3. And I think, let me just describe how to work with reflection groups. Okay, so for hyperbolic reflection groups. Okay, so now gamma is gamma is a cofinite reflection group. And P is its fundamental Coxeter polyhedron. So in fact, P is an intersection of finitely many. Okay, I will denote them by aj minus from 1 by j from 1 to n. So this is an intersection of finitely many negative half spaces. And one can associate the Gram matrix. So there is the Gram matrix. Okay, so let G of P be its Gram matrix. So what is the matrix? It is the matrix of the scalar product EI EJ so B is Gram matrix. So how does this matrix look like, right? The vectors are normalized. So we assume that EI is equal to 1. So on the diagonal, I have only units, right? The normal vectors are normalized. And so E1, E2, and so on, okay? So this is my picture. Then the angle, if they meet with dihedral angle pi over mij, I have basically 3 options, right? I can have, first I do not have enough space. Let me switch to the, I do not want to write it down very, with very small font, so let me use. Yes, yeah. So indeed, let me. Yeah, yeah. So I will write here below. We use the hyperboloid model. For HD. Okay, so we have the following options. If dihedral angle is pi over mij, where mij is this, then we write, well, then this EI, the scalar product of EI and J is in fact equal to minus cosine of this angle. If this angle is 0, which means that in fact mij can be viewed as infinity, which is equivalent to hi is parallel to hj, then the associated element is equal to just -1, right? Finally, if hi and hj diverge, then the associated number, well, it is kind of the standard metric fact from hyperbolic geometry. Then if these hyperplanes diverge, then the distance, then in fact this describes the distance between these hyperplanes. Moreover, this is equal to minus to the minus of the hyperbolic cosine of distance. I forgot did I denote it rho, right? Between hi and hj. In fact, Weinberg suggested a very nice description of Coxeter polyhedra in terms of the so-called Coxeter-Weinberg diagrams. So I can Weinberg. This language was used previously in Euclidean and spherical spaces. These are called these are known as Coxeter diagrams or Dynkin diagrams for the classification of simple Lie groups. So what Weinberg suggested, the following diagrams to use diagrams where vertices are in one-to-one correspondence with facets of codimension 1, codimension 1 faces of P, and edges describe the relative behavior, right? Relative behavior. And they do it as follows. We connect the edges, we connect the vertices labeled I and J, so associated to HI and HJ, to the hyperplanes HI and HJ, with a number Mij, or we draw an edge of multiplicity m minus 2 for small m. Or we draw an edge of multiplicity m minus 2, Mij minus 2. Multiplicity Mij minus 2. So this is for small m is used. So for m is equal to 2, this is very important. We never use an edge. These are disconnected, right? For m equals 3, being equal to 3, we just draw a simple edge. This multiplicity is usually used for m up to being equal to 6, for m up to 6, since it's possible to draw 4 edges, but it's already barely visible if you draw 5 edges. But for m2, 3, 4, and 5 for sure, we usually use the edge of multiplicity m minus 2. You see? Okay, I hope this part is clear. So if m is equal to infinity when the edges are parallel, we usually use the edge with weight infinity, or we sometimes draw a bold edge, but anyway, we will usually highlight that this is infinity. And for the last case, for the third option, we use the edge with weight minus. Okay, no, not minus, just hyperbolic cosine of distance between hi and hj. So this diagram completely describes the gray matrix and vice versa, right? So basically it gives the same data. Okay. Then, in fact, this language of diagrams, it gives the following. Weinberg shows in the same paper in 1967 that basically you can having this diagram, you can verify if a Coxeter polyhedron you're given has finite volume or is compact or neither. So then I can say the following. So the basically what Coxeter obtained is a classification of finite volume polyhedra in Euclidean and in Euclidean spherical spaces. So I will say that parabolic Coxeter diagrams so this is for Euclidean, elliptic Coxeter diagrams means spherical, right? Then Weinberg says the following: a Coxeter polyhedron P P in HD is compact if and only if every elliptic subdiagram of order if and only if every elliptic subdiagram of order. So geometrically the picture is like that. I start analyzing the edges of my polyhedron. So every edge is an intersection of how many? Of d minus 1 hyperplanes, right? One-dimensional edge is an intersection of d minus 1. So it should be an elliptic subdiagram of order d minus 1 of the Coxeter-Weinberg diagram of P. So of the Coxeter-Weinberg diagram, we can denote it as S of P. Can be extended to an elliptic diagram. Okay, to an elliptic subdiagram. Sorry, I should write subdiagram, it's important. To an elliptic subdiagram of S of P of rank D in precisely two ways. In precisely two ways. This means that every edge has two compact vertices. So the idea is that every vertex is finite. In fact, this is going to be an elementary elliptic isometry group, right? Fixing the entire ball, leaving the ball centered at this vertex invariant. And so that it's going to be a finite reflection group. But finite reflection groups are in one-to-one correspondence with elliptic subdiagrams of which order? This is just going to be a simplex. So here, this is going to be a simplex, and it's going to be a simple vertex of this polyhedron. And the order is precisely the dimension of the hyperbolic space. So you just walk along your Cox-de-Weinberg diagram of P, and you just keep verifying if this edge basically has two finite vertices. Once since you are given a finite-sided, obviously you are given a finite-sided polyhedron, you kind of have an algorithm that allows you to check everything. So in fact, you do not need to know, you basically do not need to know the vectors, the normal vectors. So this is a bit easier. If you know the normal vectors, then you can check this by using linear algebra by computations. But if you are given the Gram matrix, this allows you to check that the polyhedron is compact. In fact, there is the following and very important theorem proved by Weinberg in general. You actually need to first, so you can just draw any diagram, but nobody told you that this polyhedron with this diagram exists in the hyperbolic space, right? So I need to write the following theorem, and apparently it was probably it was first proved by Weinberg in the 70s, but so Weinberg in the 70s, that if you have a matrix of signature, okay, so if I don't know, M is a matrix of signature D1 and some number n minus d minus 1, meaning that this is the number of positive eigenvalues, 1 negative, and 0, right? Such that mii is equal to 1, and all mij's are less than or equal to 0, right? Then okay, and this is an irreducible matrix. So is an irreducible So we do not want to be like some number of blocks, right? Then there exists, okay, I will write it. There exists a unique optizometry. There is a unique optizometry unique optizometry acute angled polyhedron in HD. By acute angled, so this is, in fact, technically it should be called non-obtuse angled, since acute angled means that any dihedral angle is less than or equal to pi/2. So not strictly less, but pi/2 is allowed. Okay. So again, this is a very important theorem. So if you have now the Gram matrix, oh, sorry, okay, whose Gram matrix is M, obviously, yeah, acute angled in HD, such that G of M is, sorry, G of P is M, yeah, whose Gram matrix is this. So if you have a prescribed matrix satisfying some nice properties, and the nice properties are just having units on the diagonal, non-positive entries off diagonal, and the signature, then you have a unique optizometry acute angled polyhedron P in the hyperbolic space of this dimension D, precisely the number of positive eigenvalues of your matrix, whose Gram matrix coincides with this prescribed one. Okay. This doesn't say anything about volume finiteness or compactness. It only gives you an opportunity to find a finitely signed acute angled polyhedron. This is definitely a convex polyhedron, and all Coxeter polyhedra, like they form a like subclass of acute angled polyhedron. So if you know Gram matrix of a Coxeter polyhedron, you basically can check if this exists. And again, if you obtain some matrix, if you obtain some Coxeter polyhedron, but you only know the dihedral angles, you can find the remaining entries of the Gram matrix from this condition. It should have the signature D, 1, and some number of zeros, right? In some cases, it usually gives just some simple equation, something like the determinant is equal to 0. The determinant is not equal to 0 only for simplices. If you have a larger number of faces of codimension 1, then you definitely get the determinant is equal to 0. But you will also get more conditions, like in general, since in fact you can write down the principal corner minors of a Gram matrix, and once you, so your matrix, right, the principal corner minors, you can compute, for instance, this way. At some point you reach D+1 times D+1 submatrix. It's going to be negative, but then you add one more row and column, and you will get the determinant, the zero corner minor, right? And this is usually the way to work with reflection groups. So, okay, I think let's make just 5-minute break, and then we will kind of discuss arithmetic properties of reflection groups via Gram matrices. Okay, yeah, just 5 minutes break. All right, so yeah, let us now continue the discussion of reflection groups. So we just basically obtained, in fact, I'm not going to write it down, but there is also criterion for volume finiteness of a Coxeter polyhedron P. If you know a Coxeter-Weinberg diagram of your polyhedron, then again you start from edges, but then generally one or both of your vertices can be ideal. Ideal vertices mean that the stabilizer of this vertex is also an elementary but now parabolic group, and the associated subdiagram of this vertex can be parabolic Coxeter diagram of rank. Okay, we will call it of rank d-1 since it's associated with the horosphere of dimension d-1. So then the criterion for volume finiteness will look like that every elliptic subdiagram of rank d-1 can be extended in precisely two ways to either an elliptic subdiagram of rank d or a parabolic subdiagram of rank d-1. By the rank of those subdiagrams, we usually mean again the number of, in fact we mean the number of eigenvalues of positive eigenvalues in the associated Gram matrix. So this is in one-to-one correspondence with the dimension where this elementary group naturally acts. So again, for stabilizers of finite vertices, we act in the d-1 dimensional sphere, but we have precisely d faces, so we call them elliptic diagrams of rank d. For parabolics, we generally may have a pretty large number of facets. For instance, this can be this can look like a four-sided cone over the square in the Euclidean plane, right? Generally, it can be a cube, right, of some dimension. So it may have a pretty large number of facets. It's not going to be an irreducible Coxeter diagram. So in fact, Coxeter gave. So I should write that this is actually the work of Coxeter, right, from 1933. It gave reducible parabolic and elliptic diagrams in the spaces. So Weinberg basically now tells you that knowing the list of parabolic and elliptic diagrams is really it's a very useful result, right? It gives you an opportunity to check volume finiteness, but this doesn't check that this polyhedron exists. So this I really emphasize this fact. So in fact, you can draw a diagram and it may look like a compact polyhedron in HD, but it may be never realizable as a polyhedron in HD. So the condition that it has this signature can have no solutions, right? So then you're not lucky. In fact, this is one of the possibilities to search for new polyhedra. Try to kind of like walk through different Coxeter-Weinberg diagrams that satisfy this condition, then try to solve the equations, the system of equations, determining that it has this prescribed signature, and then you find solutions, and then you say, okay, since I found a Gram matrix, then indeed I found a good polyhedron. Okay, so now let us think about arithmeticity. So as we just discussed here, just after I announced the break, this is indeed an interesting thing about the Gram matrix. Looking at this Gram matrix, we see basically the following. Okay, in the Gram matrix, we see the following numbers, right? We see the cosine of pi over m, or we see -1, or we see this number cosh of the distance. In fact, the first two numbers are very good. These are algebraic numbers. And the only bad numbers that may appear are this, associated to the dashed edges or to the pairs of divergent hyperplanes. And there is already one kind of hint how to connect this and the number field from this board, the adjoint trace field. The adjoint trace field is about traces of elements. So I'm just showing this and then I'm switching back. And if you take the composition of two reflections with respect to divergent hyperplanes, you will in fact get the translation, right? So I will do a picture. So if you have two reflections, H1, H2, that are diverge, then the composition R2, okay, R1, R2, right, is in fact the translation along this orthogeodesic, and the trace of this translation is going to be precisely, okay, let me denote this number as A, right? And then it will be the translation with respect to the double distance between the between these two hyperplanes. This double distance, okay, the trace of this element is going to be equal to the hyperbolic cosine of 2a, right? So this is going to be an element G, right, such that trace of G is probably the cosine of 2a, if I'm not mistaken, right? So if this number, if such numbers are bad, then our arithmetic properties are not so nice, vice versa. But these elements may appear in different ways, not only just as compositions of two hyperplanes. And then Weinberg actually gives the following criterion that I'm going to write down over here. Weinberg's arithmeticity criterion is all in the same seminal paper in 1967. So let gamma be cofinite. So let gamma be a cofinite flexion group. P, its Coxeter polyhedron. Now we define two fields. So let K of capital K of P be the field generated by the matrix entries of the Gram matrix. So I will simply write, I don't know, Gij where the gray matrix of P is my Gijs, right? And the smaller, there is another field. This is which is going to be generated by cyclic products. Cyclic products of GIJs. Cyclic products are the products of this form. So G I1 I2, G I2 I3, and so on, G IS I1 for all possible cycles. So this is definitely a subfield of KFP. So for instance, Gij squared is included, but Gijs in general are not, right? So for instance, Gij squared, which is Gij times Ji, right? The matrix is symmetric, so belongs to the field KFP. Okay, then gamma is so then gamma is arithmetic. Okay, in fact, I kind of skipped the fact that let me write the lemma first, and then the Weinberg's arithmeticity criterion itself. So then it's even a proposition. If gamma is Zariski dense, is even enough to be Zariski dense. So if gamma is Zariski dense, then K of P is the joint trace field of gamma. It's a joint trace field. Of gamma, and the projective orthogonal group of the, okay, of some quadratic form of F, okay, where and POF is the ambient group, is the ambient group of gamma, where F is a quadratic form, and here one needs to be careful. So it is a quadratic form associated to the vectors okay, it's a quadratic form associated to a quadratic space spanned by vectors. Associated to a quadratic, okay, actually to the quadratic space, I guess, to the quadratic space spanned by the following vectors. The vectors are usually denoted by also V1 and so on Vs, where we write 2 to the power of S, G I1, I2, the product G IS minus 1 IS, ES, where ES is the normal vector to ES is the normal vector to the hyperplane HS defining P, bounding hyperplane. So this actually means the following. I take the normal vectors to my polyhedron P, but I scale them a little bit to make to get a quadratic space. These numbers are, it's not just like they are not chosen randomly. Definitely they are chosen in such a way that the associated quadratic space is gamma invariant. So let me write it down. And in fact, let me even okay, yeah, I think we're good. So okay, so yes, we have a quadratic space chosen in such a way that so they span a quadratic space. It should be gamma invariant. So it looks similar to the quadratic form associated to the gray matrix of P, but it's not that. The point is that if you take the quadratic form associated to the gray matrix and then you apply reflections, you will see that reflections generally may change this a little bit. I mean that you want gamma to sit in rational points of the associated group, right? But if you simply apply these reflections from gamma to the quadratic form associated to the gray matrix itself, you will get something that is generally written over the larger field, but not over this field.
So you have S as the index associated product, and you have an S on E sub S. Are those supposed to be the same S?
Well, since you need to include all, it doesn't matter. The point is that for cyclic products, you need to like it should be the full cycle. Here, it's not the cycle. It's all, yeah, it's the path from. It's like a path. Okay, one can think of this in terms of a diagram. In terms of a diagram, so we start from some from some vertex, and then you do paths to any other, to all other vertices, right? And so this non-cyclic path gives you this number, but you should also multiply it to the power of 2.
So you're
by the power of 2.
taking some hyperplane to start with.
Yes, yes, and then you can. Yeah, in fact, it does matter, but if you choose everything, you definitely are good. But yeah, indeed, in fact, you basically you pick one and then you do these paths until you get the full rank space, right? This definitely should be a full rank space since gamma is Zariski dense, right? Okay, yeah. So all right, so to construct this field now, you see you need only finitely many cyclic products, and those cyclic products are they appear from basically you can view the cyclic products as cycles of the Coxeter diagram, since this gives a just one-to-one correspondence between those cycles there and there, and the cyclic the Coxeter diagrams are convenient since you do not draw we didn't draw the edges in this case where we have disconnected vertices, right, when we have the angle pi over 2, and then it is quite convenient to write it down. So okay, Now the theorem of Windberg is the following. Well, this is essentially also like the work of Windberg. So gamma is arithmetic. Now, if gamma is cofinite, assuming that gamma is cofinite now, this is important. Gamma is arithmetic. If and only if the following conditions hold. So the condition V1, K of P is totally real. Condition V2, the gray matrix of P becomes positive semi-definite under all non-identity embeddings of the smaller field. So G of P, G sigma of P is positive semi-definite for all non-identity embedding of the smaller field into R. Well, there is a trick how to write it down. You find, again, the principal corner minors, and the principal corner minors are not written over the capital K, they're written over smaller k, since principal corner minors are the determinants, and determinants, if you write down what is the determinant of the matrix, you'll get the determinant is the sum of cyclic products of full size, right? For this concrete submatrix. Then the Gram matrix, okay, then the cyclic products gives you determinants, and since determinants describe this condition, you basically just really, you don't need the embedding. So in fact, technically, this is written as sigma of capital K to R such that sigma restricted on smaller k is not identity. But since you can rewrite this in with respect to principal corner minors, you just get elements from the smaller k, so you forget about the capital K, okay? I hope it's clear. And the condition V3 is that the cyclic products of the doubled Gram matrix, so cyclic products of the matrix which is 2 G of P, they, oh, okay, this is the subset, right? This is the subset of the O of the ring of integers of the smaller k integers. And this means the set of all cyclic products of all cyclic products. So for so assume that you have a prism as in the assignment. So what you need to do, basically, you need to compute first this dotted edge, right? It turns out that for the triangular prism, these two can never be, these two bases of this triangular prism can never be parallel. They are ultraparallel, which means that they are divergent. It basically follows from the geometry and in fact from this. you can then see that you have the condition for the gray matrix. You can write down that the determinant of the gray matrix is equal to 0. You compute this unknown entry, and then you apply this criterion. It is easy to see what are the cyclic products in this in the associated gray matrix. What are this? The squares of every weight associated to every edge, and you also include the cycle in this triangle, right? If it happens that one of these parameters, say this one, is equal to 2, you do not have this cycle at all, right? And in fact, Winberg gave many non-arithmetic examples in dimensions 3, 4, and 5, but I should definitely mention that in 1966, Makarov provided the first construction of non-arithmetic Coxeter prisms in H3. He just observed that he has a sequence of prisms where this parameter m can be any, and then he discovered that it means that starting some m large enough, you have only non-arithmetic groups. And later, Winberg just, in fact, as I remember, how Winberg told me, he just saw he attended the talk of Makarov at Stack of Institute, and then he noticed that he can suggest the entire theory for reflection groups. And then this entire theory was developed, and this allowed to get many such examples in regular way, since you can then now, you just know the criterion, and then you know how to do it. So in fact, then for reflection groups, after like inventing this theory, it became clear that non-arithmetic examples exist not only in H3 but also in H3, 4, 5, and until some relatively small dimension actually. So then it became another question basically raised: do non-arithmetic hyperbolic lattices exist in all dimensions? And the answer is yes. So now I want to discuss a little bit non-arithmetic constructions and what are the approaches to to like arithmeticity versus non-arithmeticity. And one of the first approaches to like how to distinguish arithmetic and non-arithmetic lattices was obtained by Margulis. It is the famous Margulis commensurator rigidity, right? So and to mention that this works. So gamma, if gamma is a lattice in G, then gamma, then gamma is arithmetic if and only if the commensurator of gamma in G, which is just G, in G such that the conjugation gamma G inverse is commensurable with gamma. So isometries that conjugate my lattice gamma is dense in G. And in fact, in the assignment, I gave the problem that for arithmetic lattices, one can show that the commensurator of gamma contains the group of rational points, right? And it is non-arithmetic. It is non-arithmetic if and only if the commensurator of gamma in G is a lattice, and in fact, it is a maximal lattice containing gamma. This approach, this is a very strong dichotomy. It works in the real hyperbolic spaces as well. This was actually used in some cases, I remember, for some, probably for some low dimensional. Well, it was definitely used in many cases. There are dozens of applications, but it can be used even in sometimes even in pretty like concrete situation when you have a complete description of gamma of generators. And as I remember, it was used for some right-angled Coxeter group associated to the Lobel polyhedra, if I'm not mistaken. So there are definitely many applications, but still, I would say that this is this looks like a group theoretic, right? This looks like a group theoretic interpretation. So now the question is how to what can one do to construct non-arithmetic lattices in all dimensions, and I will mention definitely the construction of Gromov and Petetsky-Shapiro. It was published in 1986. And the construction is, in fact, very geometric. So this is work of Gromov. And Petetsky-Shapiro, 1986. So they constructed non-arithmetic hyperbolic lattices in all PO D1, where D is in fact greater or equal than 2. They did it as follows. So one can, I will just draw a picture. Okay, so so we start with two arithmetic. So M1, M2 are arithmetic incommensurable. Arithmetic incommensurable, meaning that the corresponding fundamental groups are not commensurable logs. Okay, with common totally geodesic boundary. With the common totally geodesic boundary. So in fact, you start with two complete arithmetic hyperbolic manifolds, having the same totally geodesic, isometric totally geodesic hypersurface. Then you cut along this hypersurface and then glue together. So then M, which is obtained is, the totally geodesic boundary, I don't know, N, right? Since I cut and then split, in fact, I will have probably two components, right? Then this is the gluing along M is non-arithmetic. This can be viewed as, so the fundamental group of this M can be viewed as, there is a group theoretic description for this. This is an amalgamated free product of delta 1, delta 2 along gamma 0, where delta I state in lattices gamma I, and gamma 0 is the stabilizer, is the common stabilizer either of a hyperplane H that projects to this common totally geodesic subspace N, hyperplane H. Well, in fact, one needs to say something more about delta 1 and delta 2, but the idea is that it is, okay, for reflection groups, it looks like that. You glue. In fact, it's even true in general. Like you glue two polyhedra, two convex polyhedra having and the hyperplane, and basically you need a reflection sitting in both gamma 1 and gamma 2. So in fact, you glue two convex polyhedra such that this reflection disappears from gamma, right? And the stabilizer is basically the isometries that leave the hyperplane invariant. For reflections, these are just hyperplanes orthogonal to the common facet of codimension 1, and delta 1 and delta 2 are basically other guys that are not included in gamma 0, right? But something similar can be said in general. And this is amalgamated free product. It basically appears from this picture. So this gives a non-arithmetic construction in all dimensions. Interestingly, there was another construction that also uses arithmetic. And I want to mention this, since in fact Winberg suggested the notion of quasi-arithmeticity, and this construction turns out to be quasi-arithmetic. So let me define quasi-arithmetic lattices and mention what is known. So by definition, gamma in G is said to be quasi-arithmetic. The arithmetic if gamma sits in H of K for some admissible K group H, for some admissible K group H. So this means that I should have an arithmetic lattice associated with this K and H, right? But generally, so this arithmetic lattice, it satisfies this definition of quasi-arithmeticity. So this class is wider, right? So this class, so the QY class contains all arithmetic. All arithmetic. In fact, it contains almost all arithmetic since, again, there is a very special class of arithmetic lattices in dimension 3 that does not satisfy this definition with admissible lattices. This is a little bit tricky. All the remaining guys satisfy this definition with admissible groups, and in fact, so I should mention that it contains, in fact, almost all, and I will say CF dimension 3 type 3. But again, this is a very tricky thing. So the QI class is generally larger, and in fact, Winberg, in his criterion of arithmeticity of reflection groups, he also gave a criterion for quasi-arithmeticity. It's only two first conditions should hold, not necessarily V3. So for reflection groups, I will just write for reflection groups, one needs V1 and V2 only. Okay, so it turns out that there is another construction, and I will mention Agel, then Misha Belolipitsky and Scott Thompson. And in fact, it also follows from the work of Bergeron, Hegeland, and Weiss. There exists a finite volume hyperbolic manifolds HD mod gamma with arbitrary really small systole. The small systole is the length of the minimal length of a closed simple geodesic, right? So I will write it down: minimal length of a simple closed geodesic. And so the aim of this construction was actually this, but it was observed by Thompson in 2016, as I remember, that Gromov and Petevsky-Shapiro manifolds are not quasi-arithmetic, but these are properly quasi-arithmetic. That these manifolds are quasi-arithmetic, okay, are properly quasi-arithmetic, but not arithmetic, while GPS are even not quasi-arithmetic. And GPS, Gromov and Petevsky-Shapiro manifolds are not quasi-arithmetic. So in fact, we generally have kind of three large classes, right? Arithmetic hyperbolic manifolds, infinitely many commensurability classes. We have quasi-arithmetic, but not arithmetic manifolds. So low-dimensional examples were found due to Weinberg through reflection groups again. We also have not quasi-arithmetic examples, right? Also in all dimensions and also infinitely many commensurability classes. So this is a pretty large picture. In general, it is a very hard open problem to suggest an entirely new construction of non-arithmetic lattices that are, so you need to find those that are not commensurable with any of this, or are not something like simple hybrids of them. So now I want to mention also, okay, I will use this board just to save some time. So in fact, as for arithmetic, right, arithmetic classification, so we have type 1 arithmetic lattices. Those that are called of simplest type, so associated to quadratic forms. To quadratic forms, and they exist in all HD. We also have type 2 associated to skew-Hermitian forms. Skew-Hermitian forms over quaternion algebras. These are obtained in all odd dimensional, so you need to be this skew-Hermitian form. It's over R is going to be of even rank, right? So in H2 m-1, right? Odd dimensional hyperbolic spaces. And type 3, two special families. Two special families in H3 and H7. These are the only ones that contain totally geodesic hypersurfaces. So the only type that may have geodesic hypersurfaces. So those, they have even codimensional subspaces, and this type is even worse. So okay, this is a bit tricky. Yeah, this is like the whole picture. And now, like basically the idea is that what can one do with in breeding to maybe type 2 lattices to get something really new and so on. So generally, I can just mention the following result that if a hyperbolic manifold, so how one of the approaches to arithmeticity is the following. If one has infinitely many totally geodesic subspaces, so let me just write it down here. I want to mention two theorems. So one recent theorem is that if M HD mod gamma has infinitely many totally geodesic maximal totally geodesic maximal, this is important, totally geodesic subspaces of dimension greater or equal than 2. Okay. Then M is arithmetic. This is the work of Bader, Fisher, Miller, and Stover. And I think that I want to conclude with our own paper also in this matter. And this is the work of myself with Misha Belolipitsky, Sasha Kolpakov, and Slavich. It says the following: if M is a finite volume, again, it should be finite volume, obviously. So M is arithmetic if and only if it has infinitely many the so-called FC subspaces, which means that N is obtained as the projection of some plane over the stabilizer of this U in gamma, where U is the fixed point set of the finite subgroup of the stabilizer. So it's a finite subgroup of the commisurator of gamma. So this is finite. And in fact, in this case, every totally geodesic subspace of dimension greater or equal than d over 2 is FC. There is one tricky condition. N shouldn't be of type 3. So every totally geodesic subspace which is not a three-dimensional type 3, then it's harder to check. So geometrically, this definition means the following: that there exists a finite order element sitting in the commensurator such that the totally geodesic subspace is the fixed point set of this finite order element. So geometrically, in another interpretation, there exists a finite degree cover. There exists a finite degree cover where, so if I had this n here, then its lift and tilde in this finite degree cover corresponds to the symmetry of this finite degree cover, just to some finite order symmetry. So it can be not a symmetry point, a symmetry locus here, but it should be a symmetry locus in some finite degree cover. And it turns out that starting the half of the dimension, every totally geodesic subspace should be obtained like that. For these types, there exist reflections with respect to hyperplanes that fix hyperplanes and give you the FC subspaces. For type 2, one can find involutions leaving invariant, fixing invariant codimension 2 planes. And here it's also tricky, but we found involutions fixing something lower dimensional subspaces. So these are two quite different, actually, geometric approach to arithmeticity. And also one can apply to the generalized Gromov and Petevsky-Shapiro construction. And to see that in this picture, if you just take any two incommensurable blocks, not necessarily arithmetic, then this is going to be non-FC subspace. And thus, this general hybrid is not arithmetic as well, as a consequence of this construction. So yeah, I think that it's really time to, yeah, okay, it's definitely time to stop. So thank you very much for your attention. And of course, if you have questions, please reach me out by mail. Okay. Okay, thank you. Yeah, that's all.